Second step of metallurgy is extraction of metal from the ore. We know that metals of different reactivity are extracted in different ways. So we will start with the metals which are present at the bottom of the activity series. Now these metals are least reactive metals like mercury and copper. The ores of these metals are either found in the form of their oxides or their sulfides. If it is a sulfide ore, first it is converted into oxide by the process of roasting, and then this oxide undergoes reduction to obtain the metal. So first we will start with the ore of mercury, which is cinnabar. So cinnabar is the mercuric sulfide ore. Because it is a sulfide ore, so we perform roasting for the extraction. Mercuric sulfide is heated strongly in the presence of excess of air, so it combines with oxygen and form mercuric oxide plus sulfur dioxide. As soon as this mercuric oxide is formed, it undergoes reduction using the same heat as being provided during the roasting process, and we get metal mercury along with oxygen gas. We know that mercury is a liquid metal, so here also mercury is obtained in the liquid state. We will see the copper ore, which is copper glans, and it is cuprous sulfide ore. So for this also we perform roasting, in which cuprous sulfide is heated strongly in the presence of air. So it combines with oxygen and we get cuprous oxide plus sulfur dioxide. This cuprous oxide formed combines with cuprous sulfide and we get copper along with sulfur dioxide gas. We conclude that least reactive metals can be extracted in two steps. First step is roasting and the second step is reduction by heating. Now we will see how the metals in the middle of the activity series can be extracted. The metals present in the middle are zinc, iron and lead, and their ores are either in the form of oxides, sulfides or carbonates. If the ore is the sulfide ore, first it is converted into oxide by the process of roasting, and then this oxide is reduced to obtain metal. But here we need a reducing agent for the reduction of the oxide. Carbonate ores can be converted into oxide by the process of calcination, and then these oxides undergo reduction using a reducing agent like coke, and we get the metal. So we are going to start with the sulfide ore of zinc, which is called as zinc blende. As it is a sulfide ore, so we perform roasting for it. Zinc sulfide is heated strongly in the presence of excess of air, so it combines with oxygen to give us zinc oxide along with sulfur dioxide gas. Zinc oxide produced is reduced using a reducing agent coke. Now coke is a form of carbon, and we obtain metal zinc along with carbon monoxide gas. See the carbonate ore. Calamine is zinc carbonate ore. To obtain metal from a carbonate ore, calcination process is done. The zinc carbonate is heated strongly in limited quantity of air. So here it decomposes, that is decomposition reaction occurs, and we get zinc oxide and carbon dioxide gas. And zinc oxide produced is reduced using a reducing agent coke, and we obtain metal zinc along with carbon monoxide gas. But there are certain metals which cannot be reduced using coke as a reducing agent, like manganese and chromium. They cannot be reduced using coke. So to reduce the oxides of these metals, we use a more reactive metal like aluminium, which can displace these metals from their oxides, and this process is called as aluminothermy, which is reduction of metal oxides using aluminium as a reducing agent, and this reaction is the displacement reaction. So when manganese dioxide combines with aluminium, manganese is displaced and aluminium oxide is formed. Similarly, ferric oxide when combines with aluminium, iron is displaced and we get aluminium oxide. Now the special feature of these reactions is that they are highly exothermic reactions. and the heat produced is so large that the metals are obtained in the molten state. So here we get manganese and iron in their molten states. Now because of the large amount of heat produced during these reactions, they are also called as thermite reactions. The thermite reaction is the reaction in which reduction of ferric oxide is done using aluminium as a reducing agent. It is highly exothermic reaction and iron is produced in the molten state. Now this reaction has high utility. It can be used for welding of the broken parts of the iron like iron machinery, railway tracks, girders, etc. Students, we have reached the last extraction, that is the extraction of metals at the top of the activity series. At the top, most reactive metals are present, which are potassium, sodium, calcium, magnesium and aluminium. Now these metals are found in the variety of ores like oxides, chlorides, sulfides and carbonates. Sulfides and carbonates are first converted into their oxides and then these oxides are reduced. But here we cannot use reducing agent for the reduction of these oxides. For example, if I try reducing aluminium oxide using carbon, aluminium will not leave oxygen to form bond with carbon because it has more affinity for oxygen than for carbon. So its reduction cannot be done using a reducing agent. Therefore, for reducing the compounds like oxide or chloride of most reactive metals, we use the process of electrolysis. Therefore, this is called as electrolytic reduction. So, we will be starting with the electrolytic reduction of sodium chloride, and for this we need an apparatus called as voltameter. A voltameter consists of a container, or it can be a beaker, which contains electrolyte. Then there are two electrodes which can be made up of graphite here, a battery and a key. In this case, as an electrolyte we have taken molten sodium chloride, and the electrode which is connected to the positive terminal of the battery will be the positive electrode and we call it as anode. The electrode which is connected to the negative terminal of the battery is the negative electrode and we call it cathode. Now as soon as we switch on the key, molten sodium chloride will form cations which are sodium ions and anions which are chloride ions. Now we know that opposite charges attract each other. So sodium ions will start moving towards cathode, that is cations will move towards cathode, and the anions will move towards anode. Now when cations move towards cathode, which is having excess of electrons, so sodium ions will gain electron from the cathode, they become neutral, and these neutral sodium atoms get deposited at the cathode itself. While chloride ions move towards anode, which is deficient in electrons. So chloride ion give their electron to anode, form neutral chlorine atoms, and two neutral chlorine atoms combine to produce chlorine gas, which is liberated at anode. This process continues till all the sodium is deposited at cathode and all the chlorine gas has been liberated at anode. Now the sodium which is produced by this process is the purest form of sodium and it does not need further refining. Now we will see this electrolytic reduction in the form of the ionic equation. So at cathode, sodium ions move, gain electron from there, form neutral sodium which gets deposited at cathode, while at anode chloride ions are moving and they lose their electrons to anode, form neutral chlorine atom. Two neutral atoms combine to form chlorine gas which is released at anode. So this is how electrolytic reduction of sodium chloride is done. Now in the same manner we can do electrolytic reduction of bauxite ore, which is aluminium oxide. In this case at cathode aluminium will be deposited and at anode oxygen gas is released. So we have completed the extraction of metals of different reactivities.